So in this video I'm going to run through the exam questions you need to do to prepare for quiz 3. This one looks at the group 7 elements, the halogens, and there's also some more calculation questions from year 10. First one should be straightforward, it's on your carousel as well. The gas that bleaches damp litmus paper is chlorine. The next one, again this is on your carousel, something you just have to learn. It's chlorine, that's a green gas at room temperature. So you need to be able to tell me the colour of each of the halogens and whether they're solid, liquid or gas at room temperature. It's all on your carousel. The next one, the test to show the gas is chlorine. The mark scheme here is quite lenient, but I've seen it be a little bit more prescriptive, so we're going to go with the maximum detail. And maximum detail is you start with damp blue litmus paper, and the litmus paper turns red and then turns white. And they usually call it bleaches. If you turn something white, you're bleaching it. So they say bleaches white. Now the mark scheme here only says damp litmus paper bleaches white, but as I said, I've seen previous mark schemes where this level of detail is required, so we'll learn it in detail. And if you're struggling to remember the colour changes, just notice that the colours change in alphabetical order. So you're starting blue, then it turns red, then it turns white. So B, R, W, it's alphabetical order, the colours that you are listing. The next one, writing a balanced equation. So we did a bit of work of this at the start of the year. All right, so aluminium is an element, chlorine is an element, but aluminium chloride, you won't find it on your periodic table. It is an ionic compound and you'll have to work it out using the charges. So aluminium is an element, so I go to the periodic table and I see the formula is Al. It's not diatomic because no metals are. Next one I've got is chlorine. Chlorine is also an element. It's got the formula Cl. Chlorine is in group 7. All group 7 elements are diatomic, so that needs to be Cl2. On the other side of the equation, I've got aluminium chloride. You won't find that on the periodic table. You have to work it out. Aluminium is in group 3, therefore it has a +3 charge. Chlorine is in group 7, therefore it has a -1 charge. And then I'm crossing those charges over. So I write down my Al and my Cl, and the 1 that was next to the chlorine will be down next to the aluminium, and the 3 that was next to the aluminium will be down here next to the chlorine. Okay, I don't need to write the 1 though. Just be mindful that when you're doing this, it's fine to use the charges to work out the formula, but on your answer line, do not have any charges, and you shouldn't have any charges around aluminium or chlorine here because they're elements on this side. They only have a charge when they're in a compound, but don't have charges on your answer line. We just use that to work it out. So what I've written so far gets you 2 marks, but you need to balance it to get your third. 2 chlorines on the left, 3 chlorines on the right. So the smallest number that 2 and 3 divide into evenly is 6. So to make it 6 chlorines on the left, I need a big 3. 3 times 2 is 6, so the big number means multiply. To get 6 chlorines on the right, I need a big 2 there. 2 times 3 is 6. But by putting the 2 there, I now also have 2 aluminiums on the right. To get 2 aluminiums on the left, I need a big 2 there. The next one, this is in your booklet, okay, something you need to know. So we looked at reactivity of the alkali metals, and now we'll see with the halogens that it is the opposite. So the halogens, you've got fluorine at the top, then you've got chlorine, bromine and iodine, and the halogens actually get less reactive as you go down the group, and the reason is the exact opposite for the alkali metals. So with the group 1 metals, we saw that they wanted to gain an electron. Sorry, no we didn't. With the group 1 metals, we saw that they wanted to lose 1 electron from their outer shell. With the group 7s, we're going to see that they want to gain 1 electron. All right, so we're going to explain why chlorine, we'll say chlorine and iodine both want to gain 1 electron. 1 electron to their outer shell. Make sure you're mentioning outer shells. They want to gain 1 electron to their outer shell. Now with the group 1s, when they wanted to lose an electron, it was easiest to lose if the atom was big. These guys want to gain 1 electron, and it's easiest to do that if the atom is small. So chlorine is smaller than iodine, therefore chlorine is going to find it easier to gain an electron, and chlorine is going to be more reactive. And to explain why it finds it easier to gain an electron, again it's going to be the opposite to the group 1s. You're going to say chlorine has less electron shells. Don't say outer shells. It can only ever have one outer shell. There can only be one shell on the outside. Chlorine has less electron shells, so attraction between nucleus and outer shell electron is stronger. Okay, it's got a stronger attraction, and because the attraction is stronger, chlorine finds it easier to gain the outer shell electron. Okay, so that answer is on your carousel as well, or maybe phrase it slightly differently. And there are a few different ways you can phrase it. Just find a way that works for you, that you find easy to remember, and learn it off and practice writing it out, because these questions come up all of the time. The next question is actually based on this again, and it involves using your knowledge of the alkali metals and your knowledge of the group 7s. So as I said before, if I look at group 1, it goes lithium, sodium, potassium, rubidium. If I look at group 7, it goes fluorine, chlorine, bromine, iodine. And with lithium, sorry, with the group 1s, they are getting more reactive as you go down the group. And with your group 7s, they're getting less reactive as you go down the group. So if I look at group 1, the most reactive one I've got here is rubidium, and if I look at group 7, the most reactive I've got here is fluorine. Okay, and the least reactive in group 1 would be lithium, and the least reactive in group 7 would be iodine. Okay, so the reactivity trends are the opposite. And they give you a couple of different reactions here, and they ask you to pick out the one that you think is going to be the most vigorous, the most violent reaction. So for it to be violent, I want a reactive group 1, so I'm thinking potassium or rubidium, and I want a reactive group 7, so fluorine or chlorine. So I'm going to look and see if there's any reaction that has these guys paired up together. We've got potassium here with fluorine, so that's a potential that would be very reactive. Rubidium is right down the bottom, but they paired it up with iodine, which is right down the bottom here, so this is the least reactive. Potassium is good for the alkali metal, but bromine's not great for the halogens. Lithium, not very good for the alkali metals, although chlorine is good for the halogens. So I think X is my best combination. So I've got potassium, the second most reactive, group 1, with fluorine, the most reactive, group 7. So that's going to be a violent reaction. And then you need to explain why. It says explain in terms of their electron configurations why you've chosen that reaction. So what you need to do is you need to talk about why group 1 metals get more reactive as you go down the group. All right, so you'll have to talk about the fact that they are trying to lose an electron from their outer shell. And then you'll say that it's easier to lose an electron if they are bigger. All right, so if they've got more electron shells, you've got a weaker attraction between the nucleus and the outer shell electron, and it's easier to lose the electron. And then for the group 7s, you're going to be saying the opposite. You're saying it wants to gain one electron to the outer shell. So you're going to talk about having I mean, you can repeat this again. More electron shells makes it a weaker attraction, and therefore it's harder to gain an electron when the atoms get bigger. So again, what I would advise here is in your booklet you have got an answer for the group 1s and you've got an answer for the group 7s, and I would just learn them off by heart and practice writing them out. And you're going to write your group 1 answer and you're going to write your group 7 answer, and then your final conclusion will just be you picked X because you've got a reactive group 1 and you've got a reactive group 7, therefore that's going to be the most violent. Okay, you'll find the answer on the mark scheme as well, but essentially it's this 3-mark question that's come up, but they've put it in twice, one for the group 1s and one for the group 7s. The next one, boiling point of bromine. You just have to read this from the graph, so you can see that the light grey represents boiling point. Now it's obviously difficult to read this accurately, but the mark scheme is quite lenient. As long as you say something bigger than 50, so if you said 51 even, they'll give you the mark, and you can go right the way up to 70. So in between 50 and 100, if it was exactly halfway, that would be 75, but you can see that it isn't even gone to halfway, so they're not allowing you give a number greater than 70, but anything from 51 to 70 is acceptable. The elements that are solids, okay, again, this is on your carousel, so you need to learn the states of these elements. So you should learn that chlorine's a gas and bromine's a liquid and iodine's a solid and their astatine is a solid. But if you didn't remember that, you can use the graph. So we can see the melting point here, and they've given us room temperature. Chlorine melts at a temperature lower than room temperature. Bromine melts below room temperature, okay, but iodine isn't going to melt until you reach 100 and 110 degrees, therefore it will still be solid at room temperature. And astatine doesn't melt until 300 degrees Celsius, so it'll also still be solid at room temperature. So your answers there are iodine and astatine. Over here, identifying the white crystals, so you've got chlorine reacting with sodium. When chlorine and sodium react, you form sodium chloride. It's just a reaction between sodium and chlorine, and the reason they're white crystals is sodium chloride is just normal table salt, so that's what you are making there. The next few questions are from CC9, so the calculations topic. The first few questions here are quite straightforward, okay, and they're based on the law of conservation of mass. And the law of conservation of mass says if you start with 10 grams of reactants, you must end up with 10 grams of products. You don't lose mass during the chemical reaction. So saying here you start off with 8 grams of calcium carbonate. So I start off with 8 grams of this, okay? They say at the end you've got 6.213 grams of the solid, okay, which is calcium oxide. I can see that from the state symbol, and they want to know how much carbon dioxide gas was given off. Well, you know that if you start with 8 grams, you must end with 8 grams. At the moment, we've only got 6.213. So if I just do 8 minus 6.213, I work out that I must have lost 1.787 grams. 1.787 grams. And I check here in the question, have they asked for a particular number of significant figures in decimal places, but they haven't, okay, so that will be acceptable. These two together give me the 8 grams that I started with. The next one is the same. They say you're starting with 5 grams this time. They say the solid you've got left at the end is 2.8, and they want to know how much carbon dioxide. So if you start with 5 and you've got 2.8, then the carbon dioxide must be 2.2. And they've asked you to give your answer to 3 significant figures, all right? So if I've got 2.2, I'm going to have to give that as 2.20 grams, and that will be my 3 significant figures. The next one here now is a little bit more difficult, okay, because they say that you're starting off with 135 grams of this carbohydrate. So you're starting off at 135 grams, but they want you to work out how much carbon dioxide could be produced. Now we can't use the same method as before because they haven't told us how much of this product we're making. So I know that these two added up must give me 135, but I don't know how much is carbon dioxide and I don't know how much is this other product. So in these situations you have to use your moles tables that we would have done last year. So using those moles tables, it was always put 2 things in the table. You put the formula in that you've got information about. So I'm told I've got 135 grams of this, so I put C6H12O6 into my table because I've got information about it. All right, they don't mention this at all in the question, and they ask you about carbon dioxide, so I know carbon dioxide is important. And when I'm putting those formulas in my table, I don't change a thing. I keep all the numbers the same. I just don't put the big balancing numbers in. And then I do my G Mr. Moles, so mass, formula mass, moles, and ratio. The mass of this I can fill in. It's 135. The mass of CO2, that's what I'm trying to find. The MR, they've given it to you down here, so they tell you the relative formula mass of this is 180, so I can fill that in. They tell you the relative formula mass of CO2 is 44, so I can fill that in. And then you use your formula triangle, G Mr. Moles, and you'll see that moles is G divided by MR. So I can do that here, 135 divided by 180. Okay, and that's 0.75, so I can fill that in. When I want to do my ratio, that's when I use big numbers, so there's nothing in front of this, so that just means it's a 1, and there's a big 2 in front of CO2, so that means it's a 2. So if I've got a 1:2 ratio, then I need to multiply this number by 2, so that the ratio is the same, so it's 0.75 times 2, and I get 1.5. And now I know how many moles I've got. To work out the mass, if I use my formula triangle, it's MR times moles, so it's 1.5 times 44, and I get 66 grams of carbon dioxide. Okay, the next one we've got is the same. Okay, this time they want to know how much sucrose you need. They're asking about sucrose if you want to produce 26.9 grams of ethanol, and this one here is ethanol. Okay, so again, when I'm drawing my table, what they've given me information, sorry, they're asking me about sucrose, so that's important, that goes into my table. And they've given me information about ethanol, so that's important, and that goes into my table too. And I write the formulas exactly as they are, but I just don't bring down that big number. And then I do my mass, my mister, my moles, and my ratio. 26.9 grams of ethanol, so that's the mass of ethanol, so that goes there, 26.9. The mister for ethanol, relative formula mass, is there, C2H5OH is 46, so I put the 46 there. I've got mass, I've got formula mass, I can find moles, so it's going to be 26.9 divided by 46. And I get 0. And I'm not going to round that number too early, so I'll round at the end, but for now I'm going to keep that to 4 decimal places. Okay, then I look at my ratio. All right, I've got a 4 here next to the ethanol, and I've got a 1. Okay, so I've got a ratio of 4:1. So this number here on the left is 4 times smaller than the number on the right. That means this number that I write here needs to be 4 times smaller than this number. So what I'm going to need to do is divide by 4, and I'm going to again write this into 4 decimal places. And now I've got the moles. Relative formula mass of this, they give it to me here, 342. So it's that number times 342. And I get an answer of 49.9989. And it doesn't ask me for any number of significant figures, but I'm just going to round it to 2 and write 49 point, actually if I round it up to 2 it's going to end up being 50.00. So 50 grams of sucrose will be needed to produce 26.9 of ethanol. And then the last one, this is a little bit easier because they give you some of the information. They said zinc is reacting with copper sulfate, and they say this is the number of moles of copper sulfate used. So they're giving you information about copper sulfate, and they want to know how much zinc that you need. So in this case, you're taking the 2 from the left hand side. You've got zinc and you've got copper sulfate. I do my table, mass, formula mass, moles, ratio, but this time they haven't given me a mass, they've given me moles straight away. Usually I have to work moles out, but this time I don't. They tell me straight away that I've got 0.043 moles of CuSO4. I can fill in my ratio. There's no numbers in front of zinc or copper sulfate, so it's 1:1, and that means that this number must be the same as that number, 0.043. So now I know my moles of zinc. They tell me the MR of zinc is 65, and they want me to work out the mass, so it's going to be 0.043 times 65 equals 2.795. And now this time they do tell me to 1 decimal place, so it's going to be 2.8 grams. Okay, I know some of these questions can be a little bit tricky, okay, but make sure you're practicing drawing out your table. And then I think the main thing that can throw people off is just putting the wrong chemicals into the table. Let the relative formula mass help you, okay? So if they're giving you the relative formula mass of these two in particular, then it's those two that need to go into your table, okay? They did the same up here. If they're telling you the formula mass of these two, then it's these two that need to go into your table. And once you've got the right chemicals in your table, you're just following the G Mr. moles. So it's always mass divided by MR equals moles. Then you use your ratio, and then you're multiplying. So it's a divide, ratio, multiply, in that order every time.